Hi, I'm Garrett Howell, and this is Carbon Fiber. And you? So how's a dachshund similar to a sports bike? Well, if you're talking about a carbon fiber bike, they're the same weight. Carbon fiber is a material which the media and advertisers love to throw around to appear futuristic and fancy. But what is carbon fiber? As you might guess, carbon fiber is made from fibers of carbon. For more details, a piece of carbon fiber is made up of cross-stitched layers of carbon fiber, which come together to form a strong yet lightweight material, which is never found in nature. So obviously, if a new material captures the attention of so many, then it obviously must have some strengths when compared to the other materials. Also, these strengths are important in high-intensity industries such as aircraft or high-performance cars. This is primarily due to the weight-to-strength ratio that it contains. Carbon fiber samples are known to be 5 times stronger than steel, while only being 1.3 ounces per cubic inch, whereas steel is 4.65 ounces per cubic inch. And when a force is applied across the grain of a fiber sheet, it's very hard to break. Thus, once the alternatively rotated sheets are overlaid, any force being applied is running perpendicular to at least half of the sheets. The end product is an extremely lightweight material with structural capability that is similar in several capabilities to the metal solutions that are currently used, while being much lighter. Another property that is very important to carbon fiber is the lack of thermal reactivity. When placed in a high heat situations, carbon fiber tends to have much less expansion or conduction than its metal counterparts. In laboratory situations, carbon fiber has been rated on a 2, have much less expansion or conduction than its metal counterparts. In laboratory situations, carbon fiber has been rated a 2 on thermal expansion, whereas steel was rated a 7 and aluminum got a 13. And the higher the rating, the more they expanded underneath the same thermal stress. These two materials are of particular interest because they're materials that carbon fibers commonly utilize to replace. This plays a particular importance in situations where high temperature fluctuations are expected, but where the dimensions are very important. Within the same situations, carbon fiber was shown to be 10 times less conductive than steel and 40 times less than aluminum. However, of course, no material is perfect. Carbon fiber has many weaknesses that must be accounted for when being used within a design. The most notorious weakness is its anelasticity, or its likelihood of breaking when it's stretched. It's typically measured and analyzed by testing the percent elongation a standardized material sample has, commonly put into like a dog bone before it can, the percent elongation that can be done before breaking. In this instance of a pure carbon fiber sample, typically takes less than 2% elongation before fractures occur. This is according to OSHA's analysis. While carbon fiber tends to be resistant to most causes of elongation in an application, in the case it does occur, it will likely lead to a quick and brittle failure, which in most engineering applications is very undesirable. It's because it decreases the predictability of the design. And when it occurs, it's a very sudden occurrence and will likely lead to the loss or endangerment of human lives. The other major negative to using carbon fiber is the cost of both the manufacturing and the design. It's primarily because carbon fiber is not a natural material and requires a lot of specialization in manufacturing. Additionally, the process is pretty energy intensive, which increases the cost of production. Another major factor that causes the cost to go up is the lack of options for the raw materials necessary. Most of the material collection is taking place in the Philippines, with only a few companies doing the collection. This reduces the competition for price, increasing the price. The final negative for carbon fiber is because it's so variable. A lot of the properties of carbon fiber depend intrinsically on the manufacturing process that it was created in. This is because the layout of the carbon fiber sheets, the chemical makeup, and the size of the individual carbon fibers can all make major differences in how the carbon fiber will react to physical, chemical, or environmental stressors. So now you may be asking where it's used. Probably the most common areas of use are within aerospace and transportation, missiles, electronic equipment, prosthetics, and speakers. These fields are all more common for carbon fiber integration because they require they're very high intensity with extreme circumstances and high enough budgets that the added cost of carbon fiber can just be mitigated, i.e. government jobs. So, how is it made? Another fascinating aspect of carbon fiber is the manufacturing process it requires. In order to create carbon fiber, the first thing that is needed is the raw material polyacrylonitrile, or PAN. There are a few other options for base materials, such as rayon or petroleum pitch. However, they're all similar. The base material is drawn out into long fibers. That's the name. These fibers are then heated up to about 400 to 600 degrees to pull in oxygen atoms to stabilize the crystalline structure. There's a variety of processes to do this, including hot rollers, heated chambers, or just a heated gas-air mixture. Once the stretching and aerobic heating is complete, then the fibers go through an anaerobic heating at much higher temperatures, anywhere from 2,000 to 5,500 degrees Fahrenheit. The lack of oxygen is important in order to prevent the fibers from burning within these high heats. The heated fibers vibrate with such a frequency that all non-carbon atoms are kicked off the fibers. Non-carbon atoms get discharged in the form of ammonia, hydrogen, water vapor, or carbon monoxide. And then once this carbonizing is complete, the sample goes through a surface treatment in order to make it more compatible with the epoxies and various other common materials utilized to make it more compatible. This treatment includes a slight oxidation of just the surface that both chemically improves the bonding capability and changes the physical makeup of the fibers, create little ridges on the surface, which increase the area. The final step is just cutting it to prepare it for manufacturing. And this is some example of the pan fibers and the process that it goes through. And this is a machine that is used for, it's a CNC machine, but it's made for carbon fiber to prepare it for shipping. So when we're looking at any material, the impact on the world that the material has to be considered. It's because the current state of waste in our society needs to be seriously remediated. The recyclability, environmental impact, and personal safety are all important factors to consider when thinking about this. Not only in finding new ways to recycle various materials, but also in the manufacturing and longevity of these products. You need to find ways to make materials last longer and use less intensive processes to manufacture. I think a lot of future development within the environmental sustainability will be in increasing the biodegradability options of materials and improving the access to recycling processes. Processes to recycle carbon fiber are being heavily investigated right now with all the attention that's being put on it, with most of the research going into creating an inline process for it. An inline process is advantageous because it allows for a company to upsize one recycling system rather than creating a whole new one. The ability to upsize is very advantageous as it allows the system to become more profitable and last. Additionally, the quality of the recycled fiber is higher within an inline process than that of a batch process. This process takes uncured waste and then removes the resin using solvos. When analyzed underneath microscopic analysis, the samples were almost identical to the source fiber, other than the removal of the sizing. Once the coating is removed and the sample is prepped, the samples get formed into pellets that are easily used within thermoplastic composite molding. Some pieces of the carbon fiber are melted into a material that can be ran through and utilized by a 3D printer. The 3D printer is used to inject the fiber into the remaining pellets in order to increase the density of the pellets. That density makes the material more optimized for these processes. This greatly increases the profitability. Depending on the type of carbon fiber being analyzed in the system, most of the carbon fiber can be retained. However, the processes are more expensive currently than compared to the recycling of other materials. As far as carbon fiber's environmental impact, the best identifier is the carbon footprint of the material, which for carbon fiber is relatively high in the initial production method. It takes 14 times as much energy to produce when compared to a common replacement of steel. However, once the analysis goes beyond the manufacturing process, carbon fiber's environmental factors tend to increase as the weight reduction reduces the fuel drastically and they last longer than typical steel parts. The final consideration within the material's impact is the safety. In OSHA, the main safety concerns are mechanical abrasion, so scratches, and chemical irritation. For mechanical abrasion, carbon fiber can be broken when stretching, and if this occurs, the fiber becomes a fine dust of glass. This can cause irritation and abrasion for the handlers. In relation to chemical irritation, OSHA's main concern is the coating that covers most carbon fibers can cause a chemical irritation. Also, the solvents used during the manufacturing can lead to skin, eye irritations, or just combust, which isn't good. A very interesting aspect of carbon fiber is the microscopic interactions that are present within carbon fiber, arranged in a simple hexagonal crystalline structure with some atoms missing, as each carbon atom is bonded to 3 other carbon atoms. This results in trigonal planar bonding, which creates the sheet that the carbon fiber is known for. These sheets by themselves lead to slipping, hence the flaking properties of graphite. However, for carbon graphite, other molecules/materials are intermixed within this structure to create stronger bonds within the sheets. And these atoms also feature an sp2 hybridization. And here's some pictures of the microscopic imaging. So I've gone on for so long about carbon fiber, you might wonder how we came up with it. So it actually was first pioneered by Thomas Edison when he baked natural threads at high temperatures. This caused them to change into a filament. However, nothing really progressed further on until the 1960s. And in 1963, a British research center was able to invent a new manufacturing system that was able to actually realize the potential of this strength. Throughout the rest of the 1960s, research went into alternative raw materials to yield fiber from the petroleum that's created when oil is processed, because we have a lot of waste from oil creation and we want to find ways to utilize it. Then in the 1970s, further innovations were made from several companies, mainly dedicated to further improving the tensile strength. The new fibers significantly increased flexural strength and utilized 85% carbon. Much of this development was supported and encouraged by the U.S. Air Force, and thus many of the initial applications were dedicated to Air Force planes and space rockets. Some fun facts about carbon fiber is that most the raw material comes from Asia, and only 6 companies have a 90% share on the market. It's very commonly used in high-performance applications. Carbon fiber products can be repaired. You just have to find an expert who knows enough about it to successfully do it. And carbon fiber is also RFID blocking. So that's why some wallets are made out of carbon fiber, so you're protected from credit card skimmers and other threats like that. And carbon fiber can also reduce the average cellular signal by 40 to 60%.